An airplane propeller is rotating at 1860 rpm or revolution per minute. So we have to compute the propeller's angular velocity in radian per second. And we have to compute how many seconds does it take for the propeller to turn through 40 degrees. So for A, we have to convert it into rad per second by multiplying it to 1 minute over 60 seconds to eliminate a minute, and we have to multiply it to 2 pi rad over 1 rev to eliminate rev, so that would be remain, and that will give us 62 pi rad per second. And for B, we have to convert degrees into rad first. 40 degrees is equal to 2 pi over 9 rad. So in order to get time, we have to use the formula of angular velocity equals to angular displacement over time. So we isolate time, and that will give us an equation of time equals angular displacement over angular velocity. And now we have to use the computed angular displacement, which is 40 degrees in rad, that is 2 pi over 9. And we have to divide that by the angular velocity of 62 pi rad per second, and that will give us an answer of 0.0036 seconds. The angular velocity of a flywheel obeys the equation of a plus b times t squared, where t is in seconds and a and b are constants having numerical values 2.75 for a and 1.60 for b. So now we have to determine the units of a and b if the angular velocity is in rad per second. And then we have to calculate the angular acceleration of the wheel at time 0 and time 2.5 seconds. And then we have to answer the question, through what angle does the flywheel turn during the first 1.8 seconds? So for A, the unit of A is rad per second, and in B, the unit is rad per second cube, in order to eliminate the s squared in t raised to 2. So now we have to compute for the angular acceleration, and we'll be able to do that if we multiply um, b, which is rad per second cube, multiplied to time, which is s, so that only s squared would be remain, because the unit for acceleration, angular acceleration, is rad per second. So when time is 0, you multiply 1.60 rad per second cube to second, which will give you an answer of 0 rad per second squared. And when time is 2.5 seconds, you'd, you'd be able to have 4.0 rad per second squared. So now we have to compute the angle of the flywheel during the first 1.80 seconds. So in order to do that, we have to integrate the equation of a plus b times time squared. So the integrated equation of that is um, at plus bt cube over t 3, and then we have to plug in 0 and the time, which is the upper limit, which is 1.80 seconds, and the lower limit of 0 seconds, and that would give us the equation of 2.75 rad per second times 1.80 seconds, which would be cancelled, I mean, which would the second be cancelled, and you add that to 1.60 rad per second cube multiplied to 1.8 seconds raised to 3 divided by 3. The seconds, all seconds would be cancelled out. You'd be able to remain, there would only be a rad in the equation, and that would give you an answer of 8.06 rad. So for the last item, a fan blade rotates with angular velocity given by gamma minus beta times time squared, where gamma is 4.85 rad per second and beta is 0.79 rad per second cube. So first, we have to calculate the angular acceleration as a function of time. And second, we have to calculate the instantaneous angular acceleration at time 3.50 seconds and the average angular acceleration for the time interval 0 to 3.5 seconds. And how do these quantities compare? And if they are different, why? So first, we calculate the angular acceleration as a function of time by using the equation gamma minus beta times t squared. Then we have to derive the equation. Now we will have negative 2 beta t. Then we have to plug in the beta in time. So now we have to multiply negative 2 to 0.79 rad per second cube, and then the time would be remain because we have to compute the angular acceleration as a function of time. So now we calculate the instantaneous angular acceleration using the derived formula which we used the first part. So now we have to plug in the time, which is 3.50 seconds, in the equation, and that will give us an angular acceleration of negative 5.53 rad per second squared. So now we'll compute the average angular acceleration. So when time is 0, um, you will have a angular velocity of 4.85 rad per second. And when time is 3.5, you will have the final angular velocity, which is negative 4.83 rad per second. So now we compute the average um, angular acceleration by using the formula of final angular velocity minus initial angular velocity over final time minus initial time. So we plug in the solved final and initial angular velocity, and we would be able to obtain an average angular acceleration of negative 2.80 rad per second. So the instantaneous angular acceleration, which is negative 5.53 rad per second squared at time 3.5 seconds, is double the magnitude of the average acceleration, which is negative 2.80 rad per second squared between 0.0 seconds and 3.50 seconds. So these two quantities differ because the angular acceleration changes as a function of time.